All right, so we need to be able to look at molecules that we haven't seen before and say, are these going to form something that looks kind of like an enolate? And is this going to be easier, faster than a standard enolate, slower? How acidic is that proton? So what we have here are three of the things that we've talked about recently, what their pKa values, what their conjugate bases look like. And we can, again, rationalize why they look like they do. And remember, compared to CH4, where the carbon bears all of the negative charge in the conjugate base, when we deprotonate this position, it forms this enolate that is a mixture of the negative charge on the carbon and on that oxygen. This one here, we could draw it really looking like a mixture of three resonance structures where there's partial bond character, partial pi bond character between all those positions, partial minus there, and partial minus there, which really delocalizes that charge and drops that pKa value to about 10. So where do all these fit in? So now would be a good time for you to pause the video and start filling in the blanks up here. Okay, you've done that a little bit. It's always nice and easy to check off boxes that we already know about. So this one here is on our pKa list. That's a carboxylic acid. It has a pKa of 5. Why is that? That's because the negative charge is shared between two oxygens. Remember, oxygen's more electronegative than carbon, so sharing the negative charge between the two oxygens is going to make that really stable. What else? So this hydrogen here, if it were deprotonated, it would have a negative charge there that was also delocalized to that side, but it's on two different carbons. So where would that be? That's not going to be that stable of a conjugate base. It turns out that it's going to be pretty close to CH4. So we can draw that here. The conjugate base would look like this, which also is delocalized onto the other carbon. But again, carbon doesn't like negative charge that much. It turns out its pKa is about 43. What other one do we have up here that would be not very acidic? Yeah, which of these is not very enolate-like at all? Yeah, this one here, right? If we deprotonate there, the negative charge is here, and it's blocked by two different sp3 hybridized carbon atoms, so it is not delocalized whatsoever. So that one's going to be really similar to that CH4. I don't think anyone's actually ever measured the stability or the acidity of this proton here, but it's going to be somewhere between, we'll say, 43 to 50 as pKa value. And again, why is that? That's because the anion is just on an island here, all by itself on that one carbon atom. Okay, so now we have an ester versus an aldehyde. So what we want to think about is if we have a negative charge, if we were to deprotonate this aldehyde and we had a negative charge right there, how does that compare to, say, this negative charge here? Is the negative charge stabilized or destabilized by having a CH3 in this position? Well, is a CH3 electron donating or electron withdrawing? Okay, yeah, CH3 donates electron density by hyperconjugation. So that means that this CH3 that's here is actually adding electron density to a negatively charged area. So it's making this negative charge more negative. That's not going to be ideal, right? If we compare that to this negative charge here, it's just a hydrogen. A hydrogen isn't very, there's not a bunch of hydrogen bonds that can hyperconjugate. In fact, this hydrogen can't hyperconjugate at all because it's not in the same plane as that pi bond. This does not hyperconjugate. It doesn't electron withdraw either, but compared to this one that does donate electron density to the negative charge, this is going to be more stable because it doesn't have anything donating electron density to that. So this is going to be more stable than that. We'll draw it right here. This is more stable than that, and it has the same two resonance structures as that enolate. So if it's more stable than that, then it means that it's going to be more acidic than that. So we're talking about this hydrogen here. It's got a pKa of about 18. So it's not an enormous impact, and actually I just looked down at my notes. I thought it was 18, it's 17. So not an enormous impact, but an impact nonetheless. What about if we had an ester? How does this oxygen here impact the negative charge there and there? Does that oxygen donate electron density or withdraw electron density? Yeah, it does both, right? If we're thinking about induction, induction is pulling electron density away in sigma bonds. It does that, but also it does resonance donate, right? We can draw those electrons moving up to there and up to the oxygen. And what usually wins, resonance or induction? Yeah, right? Resonance almost always wins. It's like super rare that resonance doesn't win. So this oxygen donates electron density, puts more negative charge on an area that's already negative. That's going to destabilize it. And resonance beats hyperconjugation. So if we're talking about how stable this is, it's going to be less stable than that anion there. So we would put that ester above this as far as the stability goes. So something like that. So its pK is going to be higher than 20. And I think it's 25 when we look down at my notes. Yep, 25. So the only one we don't have left, so we did that one, we did this one. The only one we don't have, that we haven't done yet, is this nitrile. How is that going to compare? Go ahead and draw the conjugate base, draw any stabilization that has. Yeah, it has that same resonance delocalization, right? If we deprotonate that hydrogen, that would give us a negative charge on a carbon that is bonded to that carbon, that is the triple bond there. So we can show resonance delocalization. I'm going to draw the other resonance structure up here just because I'm out of room, where we would have the CH2 double bonded to a carbon, double bonded to a nitrogen that's negatively charged. It'd be kind of hard to rate where this is going to be in the context of the rest. It turns out that that CH3 C triple bond N actually has a pK value also of 25. So it's similar to that ester. And we can rationalize that it would be less acidic than the ketone, right? Because if we have the negative charge on an oxygen versus a nitrogen, the negative charge is more stable on the more electronegative element. So it's more stable on that oxygen compared to that nitrogen. Which means that this molecule here, this enolate equivalent, is less stable than the one we started out with, this here, less stable. So if it's less stable, that means that the acid is less acidic. So that's why it is 5 units higher than the pK of this guy here. So that's kind of how you can kind of fill in blanks by looking at the conjugate bases, saying how stable they are and relating that to the acidity of the proton that would be removed. Again, why is this relevant to this chapter? Well, we are adding electrophiles to enolates and enolate equivalents. So if an electrophile is able to add to this position here, it's likely that it's also going to be able to add to the carbon of this enolate equivalent there. So we have to be able to kind of recognize this can form an enolate that's going to look like this, and if we add an electrophile to that reaction, it would add to this position.